storm palm is inherently elegantly paralyzed. You don't need any structure and so on. You just may have to make sure that the next molecule is further away than the diffraction barrier. It's instantly paralyzed. It's one of the reasons why it has become so successful. Now, this one is dedicated to Xiaowei. I think a very important discovery that was made with Storm was this arrangement of the actin structure in the axon. Now, if some of you had doubts about the structure, here they are with that. And so very clear, very beautiful. And again, it required the breaking of the diffraction barrier, the super resolution, in order to see these details, as has been nicely shown actually in Xiaowei's study. Now, a few more insights. PSF, OTF. If you have an optics background, point spread function, transfer function. What happens with the point spread function, transfer functions? Of course, in both of these methods, the point spread function is sharpened. Not just in this one, also in this one. They are both sharpened. They have to be sharpened because the point spread function is a function, a linear function that, or the imaging is a linear function that has a function, namely the point spread function, that tells us how an object, a point-like object, is relayed into the image. And of course, Palm, Storm, and STAT have point spread functions, which is not, by the way, the diffraction pattern that you have on a camera or on a detector. It's a complex function of the molecular state. So this is very important. So just with waves, you won't be able to describe neither the point spread function of the STAT nor that of the Storm Palm. They depend on the stochastic molecular state transition, but both sharpen the point spread function. And this must be the case. Otherwise, they would not be valid as imaging methods. Another insight I would like to give you. We can instantly agree on the fact that this STAT resolved is a nonlinear optical modality, if you like. You can say that we use a saturated transition in order to get here. But then, Palm Storm, would that be a linear modality? Doesn't make any sense. Why? Because it uses the same molecular transitions. How can this be nonlinear and this linear if they use identical molecular transition? Doesn't make any sense. So if you think about it from the optics viewpoint, then you realize that, of course, Palm Storm is also nonlinear. But there is a major difference in nonlinearity. Here, the nonlinearity stems from the many photons that produce a single event, namely the localization here. So this is nonlinear in terms of the photons that come out, and this is nonlinear in terms of the photons that go in. So that's the point. You need the many photons to find where it is. And here also, you need many photons in order to determine the position. A single photon cannot be used to doing anything about positioning. Why? Because a single photon that would be coming out of the laser and go here would go astray, would go this way or that way, we don't know. You need many photons to set up this difference in state and to determine the position of the emission in a STAT or resolved microscope. So you need many photons. It's not just working with one photon. And this is, so to speak, the fundamental requirement. Just as you need many photons to come out from the sample in order to determine the position. With one photon, it wouldn't work because the one photon could come from anywhere within that region. So when it comes to positioning, finding out position or defining positioning, you have to use many photons, m photons. That's the point. But that's just the position. That's just the position. The separation is, of course, very important because, as I said, we need to tell things apart within this 200 nanometer range. And the separation is, of course, done by a state transition. As I said, loosely, by playing the on-off game, on and off. This is how we are able to tell things apart. And on and off is, of course, represented by states. A bright state and a dark state. A state that is capable of sending light back and a state that is not capable of sending light back. And once you realize that, then you know that this is a rather, say, fundamental principle. You can have many, say, state pairs, as you've seen here, that allow you to play these games with many advantages and disadvantages, different lifetimes and with different chemical requirements. But in the end, it's the same story. And of course, you could have fluorescent and non-fluorescent, but it's not fundamentally tied to fluorescent and non-fluorescent. So it could also be absorbing, non-absorbing, scattering, non-scattering, spin up, spin down, green, blue, bound, diffusing, still, moving. And I think we've seen already first studies that actually push those principles away from fluorescent. I'm sure this will come. There will be people coming up with clever ideas to have super resolution, not only in the fluorescent case. And with that, of course, I'm coming to basically my final slide. Well, as I said, towards the 20th century, People believe that the end of the world in a far-field optics is the confocal microscope. That's the best spatial resolution. We know now that we can do much better. We can, of course, expand this equation very easily, plugging in the square root factor, and now we know that we can get the d down to the size of a molecule, so down to 0. The point that I'm making here is, why can we separate now this strand from that strand, but we can't do that here? Well, it's very simple. At a time, they were, say, flooded with excitation light simultaneously. The molecules of this feature were in the S0, whereas in that feature, they were in the S1, and then vice versa. This is why we can separate them. That's the point. And so, what I'm saying is diffraction barrier is broken by preparing the molecules of adjacent features transiently in 2 different states. Of course, you can do more states if you want, but 2 states are enough. With 2 states, you can fundamentally overcome the diffraction barrier. And all these, say, terminologies like point spread function, optical transfer function, passband, nonlinearity, they become dodgy. Why do they become dodgy? Because they were coined with waves in mind. Point spread function, transfer function, passband, this has waves, and the waves should go through the opening of the lens. Nonlinearity is always about number of photons, usually. And so this is, these concepts become dodgy. And this is why I'm saying do away with them. They made a lot of sense. You can still work with them, but it's time to give them up. It's thinking of the 60s, 70s, 80s of the last century. Think about it differently. Resolution is not just about waves. It's about waves and states. And I'm convinced that future generations, when you think about a light microscope, they will not just ask for, let me have the best waves and the best lenses, constant best waves. They will say, are there any states in my sample that give me nanometric scale resolution? This is the way you should see the light microscope. And there are already people who do that, not at least the ones in my lab. And by acknowledging them, I would like also to thank you for listening. Thank you very much.
Thank you, Stefan. Time for questions.
Okay, well, thank you very much, Stefan, for the great talk. I'm a little confused about why you make this big point about nonlinearity in the way you do. I mean, it's a beautiful aspect of STED that it's the saturation of the process that makes the effective size of the donut get smaller and smaller. It's just beautiful. And every one of these functions, like that one, do not have intensity to the first power. So I agree with you that that's intrinsically nonlinear. And that's what you said. STED is intrinsically nonlinear. And so, but when you say single molecules is also nonlinear because of the photon business, I think you can also view it as being nonlinear in intensity space for the same kind of idea. I mean, as long as the molecule is emitting and you haven't saturated it, signals, of course, will be linear. But when it turns off, you get no light. So, I mean, that's the deepest nonlinearity in a sense. And another way of thinking about it is when you have lots of molecules in a spot, and with one on and all the rest off, that's a higher order correlation function, that all of those are off and one is on. And so the in-molecule correlation function has to be intrinsically nonlinear in intensity. So I don't know why you have to, I just don't understand why you make the distinction the way you did.
Yeah, a very good point. So I'm not saying that nonlinearity is, of course, wrong, in no way. So definitely, you can explain everything, say, in STED or resolved in nonlinearity. But I'm saying that the nonlinearity view is not the best way of seeing it. In the end, it's all about the transition. What you do instead is you make sure that the molecules get to a different state. And of course, you want to get it everywhere except maybe in one particular place where you have one molecule, a few molecules left. It's just a transition. That's the only thing what you do. There are other types of nonlinearities, as you all know, multi-photon excitation process, things like that. They have little or nothing to do with the process that we do here, namely just a state transition. Why should I use a concept like a higher concept such as nonlinearity if I don't have to use it? If you just can say, the only thing I'm doing is shifting the molecule from one state to the other, and that's it. By that, I'm just separating the features. That's the story of STED and resolved, just making a transition. Of course, you can always argue inherently a transition is something nonlinear in terms of the photon, because once it's there, it's there. You can see it that way, but I think nonlinearity doesn't get me any new insight in this particular case. And of course, I can also see in the Palm storm is inherently a nonlinearity, because what you do is, of course, you do a transition, you have a switching, you go from, say, from an off state to an on state, you make definitely sure that it goes to the other state, but then you don't know where it is. And what you do is you localize it. You take, of course, many photons. You need them, critically need them, to find out the position, and that is nonlinear in terms of the photons of the order m. And this is also why the images have zero background or very low background, because you make out of, say, m photons, you make out one event. And so what I'm saying is there is a clear analogy in having, say, nonlinearity, using many photons to make sure that the threshold moves in, and of course, taking many photons out in order to make a single event, namely that localization event. And seeing it that way helped me, and that's my point, helped me understand the whole, not only the field, but also tell you the weaknesses and the strengths. You can see instantly. I cannot see how you could infer from nonlinearity that in the resolved and the stat case you need many on-off cycles. I cannot see how you can infer from that. But if I see it that way, I can instantly tell you this concept, stat resolved, needs many on-off cycles, but not many photons. I couldn't infer that from the nonlinearity concept. You see? But from a state transition concept, I can instantly see it, or Palm, storm, vice versa. I can instantly see that I need many emission cycles in that concept, but just one on-off cycle. So the ability to fully explain things without having conflicting thoughts makes me put it that way. And again, if you coin, for example, stat or resolve nonlinear, but then Palm or storm nonlinear, ask, how come that they use the same transitions? They use a cis-trans or a ground state depletion or so. They use the same molecular transitions, but why would that be linear and the other nonlinear? So I'm saying it's not a good concept. We should forget it. We should try to look what it is. We just make a state transition to make things separable. In one case, you put in the photons to make that state transition, of course, in such a way that we determine where it is. The other way, we do it stochastically and get the photons out and determine the position. That's it.
I like people asking questions. First, identify yourself, stating your name and names and institutions, please.
And what? Name and what?
Institution.
Okay, I'm W.E. Marner. I'm from Stanford University. Well, let me put it a different way. If your fluorescence depletion curve as a function of intensity were linear, then you wouldn't be able to make STED work very well, because you actually need to have that saturation phenomenon in order for most of the molecules to be off, right? And so, you know, you need to embrace it. I don't see really why you feel like you can't just embrace it.
W, there's a misunderstanding. I'm not saying, I'm not saying it's not there. I'm saying it is there. Of course, I'm constantly showing thresholds. And of course, anyone who has a training in optics knows threshold means there's a nonlinearity. But you don't need this idea of nonlinearity. The only purpose of that transition is to get it to the other state. And I won't be able to be sure that it's in the other state unless I've put in a number of photons, because the cross-section is finite. So I always need a certain heap of photons, say 10,000, to be sure that's in the other state. Because I'm making a state transition that makes my feature separable. For that, in order to make sure that it happens, I have to use a certain amount of photons. That's it. And if you want to call that linear, okay, fully agree. You can call this nonlinear. Fine. But why should I use this terminology if I don't need it? You just need to say I have to push it to the other state. That's it. So my point is, it is kind of not to the point. It makes you think about multiphoton and all kind of things, and this has little to do with that. People in the past thought, oh, well, maybe with multiphoton, especially physicists, one can go beyond the diffraction barrier, but no one could show images. Why? Because it's saw the wrong way. They always had photons in mind. I need to have many photons to put them in, and then finally I will get something. But it never worked. The state transition, that was the key.
Stefan, Rafa Yuste from Colombia.
Yeah.
I have a comment on, you mentioned the power that the NV centers have as ideal dyes for super resolution microscopy, and you mentioned that they're sensitive to magnetic fields. I just wanted to let the audience be aware of the fact that they're also among the Earth's most sensitive material to electric fields, which means that they could be the ideal material to build voltage indicators in the future.
Yeah, very interesting. And the question is, how does it relate to fluorescence? If you can read it out, say by fluorescence, STED may be a way to read out the electric fields. So there's a lot of potential. And of course, temperature. Misha Lukin published very recently using the NVs for very sensitively measuring temperature.
Please.
Hello, I'm Roberto Echenique from University of Buenos Aires, Argentina. You show that you can, with STED, to see the magnetic states of molecules that are very close. Do you think it is possible to get some kind of insight of quantum computation using this kind of magnetic imaging?
I mean, this is one of the reasons why these NVs are currently investigated so heavily. They are among the best, or perhaps the only candidates right now for single qubits at room temperature. And this is interesting. Of course, one can think about using, say, a sub-diffraction resolution imaging technique such as that in order to read out qubits that are very close together. So there is say, call it thoughts about it, speculations about it, but that has not come to a stage of development where I would commit myself that this would eventually work.
Stefan, I have a question. Sunny Xie from Harvard. Also about the linearity. Now, let's say at the, if you have a tiny sample, if my interest is to determine the number of molecules with certain resolution, right? So I was just thinking about this while you were talking. I think I know the answer, but I want to confirm with you. Now, in the case of storm or palm, since I'm counting individual molecules, so the counts are proportional to the number of molecules. Now, for resolve, I mean, this scheme, since you do have nonlinearity and the conversation about, I mean, it's the same transition, right? But in practice, is there any nonlinearity that gives you a signal that is not proportional to the number of molecules? I mean, in addition to resolution, I still want to know the, say, stoichiometry or just the number of molecules, quantitative microscopy.
So in all these methods, the signal, of course, that you get in the end is proportional to the number of molecules. So it is a linear function. So that what you get, the image, is a linear function of the local concentration of molecules. That applies to STED, resolved, palm, storm, and so on. And this is why you can have a point spread function. So this linearity is always there. And of course, this must not be confused with the nonlinearity discussion that we had before, in the sense that you use many photons to make a well-defined transition in space, or to define the position of a state in space. I don't see the risk of having an image that is not proportional to the number of molecules in none of these methods, unless you have other effects like strong photo-bleaching in both methods, palm, storm, and STED, and so on. And then of course, then you introduce a kind of history into your samples,
so,
then you have this risk. Otherwise, there is no risk.
You wouldn't have it in certain intensity range, or maybe at the, I mean, you would. Okay, I think I.
No, it's not the intensity.
That's what I thought the answer. I just want to make sure.
What you do actually here is you do a transition. You do a transition, and of course there's two states. And of course, if I'm going from one state to the other, in the end, I'm sure that I'm in the other state. Of course, you can say this is nonlinear because you don't need any photons anymore to get there because you are there already. But it's just a transition, and this is why, personally, I feel I thought about years about this, and I really stand to this view. Nonlinearity, although it's valid as a concept, you can explain everything, doesn't get you to the point, and it doesn't get you further insights, and doesn't definitely not describe to you mathematically, beautifully, what the power and the limitation of each of the techniques we've seen is. And this is why I tend to give it up, but of course I'm explaining in such a way that people understand it and try to get away from that thinking. I think this is how it will go down in the end in the books, because this is what it is. This is why I'm saying so plastically.
Thank you.
Yeah.
Hi, Stefan. This is Paul Sullivan from the University of Illinois. a very nice talk. What I'd like to understand is the second beam, which you're effectively causing, lasing back down from the excited to the ground state. The question is about the photostability of the dyes. And have you gone through and looked at a particular number in terms of, which dyes are effectively photo-bleached by the intense beam and which ones aren't?
There's no general rule, Paul. I cannot really give you, say, a general rule of saying, okay, now this dye should be fundamentally better in all cases, and this would be worse in all cases. Of course, in the case of STAT, if you refer to that, but that applies also to the other methods. There's not just the S0 and S1. There are other states. There are triplet states, there are high-lying states, and of course the molecule may end up in these states and may do something that you don't want. May either blink away or entirely bleach away. I can only say what has worked, because we do many, many experiments and many, many wavelengths, many, many dyes, and as time has passed, more and more and more things have worked. If you go down to the very early papers, you will see that the first 10 papers were made with a single dye, pyridine 2. And people thought, oh, that method would work only with one dye. And now you see, fluorescent proteins with even quantum dots. Initially I thought maybe that's a problem, wouldn't work. Now I know that it works. And so by doing the experiment, trying out different things, different pulse duration, different wavelengths, different powers of excitation, I mean, this applies to STAT. You sort out more and more things, and you know what works, and you do what works. But of course, one has to do it. One has to try all states. And the same applies, of course, also to the stochastic methods. You have to have, of course, molecules that emit many photons in a bunch after you got them to the bright state, isolated, and this will not be the case for everyone.
Absolutely. So in particular, the case of the fluorescent proteins,
sure.
With POM and STORM, people have carefully optimized them to be photostable enough to give you a signal.
Yeah.
And so how does that work in terms of the fluorescent proteins, for example? What kind of resolution can you get?
I mean, in the STAT case, we get down in the living cell conditions to about 50, 40 nanometers. If everything works well, especially the yellow fluorescent protein turned out to be well. GFP also in that ballpark, slightly worse than the yellow fluorescent proteins. But there's the resolve concept. You have the switchable fluorescent proteins. You don't put so much light. You did orders of magnitude less light. You have to get the cis trans working properly. It goes back and forth many times. Once that's sorted out, you can go even further down. So best we had there was something like 25 nanometers. It's not the end. It's the beginning of the story. And this, again, why I believe, and really mean it, it's important to understand the basics of it. You really have to understand, when I want to have a palm storm dye, it needs many emission cycles, because that will ultimately give me the spatial resolution. It need not go on and off many times if I want to take just in many emission cycles. And vice versa, in the resolved method, I don't need to have very bright dyes as for palm storm, but I need to have many on-off switching cycles. This is why I'm very much trying to persuade you to look at it in this way and give up all the concepts of thinking, because this is what it is. And this really explains us why you have to develop dyes like that and like that. In fact, we have dyes, switchable fluorescent proteins, that work wonderfully with resolved, but they don't work for the stochastic method, and vice versa. Because the two methods have different requirements. They are based on the very same principle of state transition that makes it distinct, but then the way you make the position is different. In one case, the photons that go in, so you need the transitions. In one case, the photons that come out, you need the emissions.
Okay. Thank you.
Hi, Stephen. This is Peng Xi from Peking University. I have a comment on the nonlinearity that Sunny has just raised the question, and I would like to have your idea on that. So the term of nonlinear comes originally from multiphoton process, and if you think about multiphoton, you realize that the excitation of one 800 is modulated by another infrared to get So if you compare the original PSF generated from the 800 versus the fluorescent is actually so-called super resolution already. But well, it certainly cannot compete with one single 400 nanometer excitation. But we through multiple multi-photon process, it's doable that we can get better and better resolution in comparison with the original excitation point spread function. And so when doing the multi-photon, we have multi-photon in, but one single fluorescent photon out. So we lose a lot of photon. And instead, so PALM and STORM, it has the same thing. Instead, we modulate them down. We turn it off, switch them off. And in PALM and STORM, it's like an histogram, and we only take those few photons on the bottom of that, so we can localize them. So again, multi-photon in, one photon out. So I think the nonlinearity might come from that kind of process.
But my point is, if somebody here of the younger generation hasn't heard anything of nonlinearity, you can beautifully explain the power of super resolution without using the word nonlinearity. You will get absolutely to the point without any restriction and fully explain why the method here is strong with those dyes and strong with that dyes, and you fully explain it. You don't have to use the word nonlinearity at all. And this is the point that I'm making.
I agree. Thank you.
And I think that your generation will think like that because they will grow up without the historical, say, burden.
No more questions? Please join me to thank Stefan for a very exciting, very stimulating keynote lecture.
Okay.
I guess the bar is open. Tomorrow morning we're going to start